All right, so now we're going to start sort of a new section where I'm going to be explaining to you how to make medical instruments that measure how much of something, like how much glucose do you have in your blood, how much oxygen do you have in your blood, and so on. And in a way, you would think this is almost where we would start, right? I think usually when you think about measuring in biomedical, it's like how much of something, right? But we waited until now to get there. And we're going to start with something that I demoed I think very early on in the class, which is this thing, which is called the pulse oximeter. It measures pulse, and it measures the amount of oxygen in your blood. So it's measuring right now, and it's saying my heart rate is 83. All right, I know you can't see what it says. And it also says percent SpO2 is at 97. And we're going to talk about what that SpO2 means and how you're going to make a device, right, that's capable of also measuring SpO2, which is how much oxygen is in my blood, all right, specifically in my body. Make sense? And in the hospital, I remember, right, one of the earliest classes, I said, well, often the devices look something like this, where they tape it to your finger, right? And now you know, sensor, cable, and then this plugs into the circuit, right? It's the same thing. It's the same thing. And just in this case, the cable is very short. And in fact, it's the same thing as the one that's on my watch. So if I activate it now, it's going to try, right, to measure my oxygen, right? So Apple has this product as well, unsuccessful measurement because I moved. And if you play, I don't know if you can tell, but if you've ever seen these watches before, you'll actually see that there's lights flashing in here. Or if you were to look inside of here, it's hard to tell. But if you were to look inside, let's see if we get it going. And if you can tell, but there's like a little light flashing in here. So that gives you one clue about how these things might work. Hopefully by the end of today, you will all be clear about how that happens. Okay. We also talked in the start of class that generally speaking, a technique that is used for measurement can be invasive or it could be non-invasive. Invasive basically means it has to go through the skin. Might use the word transdermal. All right? So if I have to stick a wire inside of your body to measure your blood glucose, I would call that invasive. Maybe people would use the term minimally invasive, but it doesn't matter. You're piercing something through the skin, and that's a big deal. If I need to draw blood, right? So if we're taking a sample of blood, that right away involves a level of invasiveness, and we're very familiar with that. You go to your primary care provider, right, your PCP, and they're going to draw blood, and then they will send that blood to somewhere else to do a test. It's still invasive in the sense that you got to get through the skin to extract it, right? An example of a non-invasive device is what you just saw here, right? This is a non-invasive device, and you can see the appeal of a non-invasive device. You get an immediate reading. I don't have to poke you, right? So it's very preferential, right? Especially you can imagine trying to make a watch like this, right? Where some person had to insert something into their body. It would never work. If you, like with the COVID test, have to sample mucus or spit, that remains non-invasive, all right? Because you don't have to penetrate the skin. So that's still in the non-invasive, even though you're using an orifice in this case, okay? So you have invasive and you have non-invasive. And we're going to focus, as we always do here, mostly on the non-invasive types. Okay, and so let's talk about non-invasive. Let's take a finger. Draw a finger here. It's like a fingernail. Here's a finger. If you were to take a light source and shine it through the finger and look on the other side, perhaps you've all done this, right? You would see all this red light coming out the other end, right? You ever put a flashlight onto your finger and you looked on the other side and you saw something red coming out of the other side, right? Right? Because there's red stuff inside our bodies, and so light partially goes through the body. right? Now, what would you use to make a light? Do you have anything in your toolkit you could use as a flashlight? An LED? Yeah, so we already have that. We don't need to add any new tool. So you would take your LED, you would connect it to a battery, as you know, put a resistor so you don't blow it out, put it up to your finger, and you're actually going to see light coming out the other side. Now, we're going to add onto this side a light sensor. Now, there's that word sensor. We've seen it before, right? Now, I defined in this class, right, that a sensor is something that converts your measurand into an electrical quantity. Remember that definition? That's a sensor. This light sensor, which there's different kinds of it. Sometimes they're called photodiodes. It will detect some amount of light, and there's less, by the way, showing up here, right? Because some of it's not going to make it through. And it converts that light into a voltage. So this voltage is a function of the light that arrives. So you can imagine if there's more light, you get more voltage. So this is just something you can buy it. It's just called a photodiode. It has two ends on it, just like all sensors. You see, oh, it's the same thing all over again. Yeah, it is the same thing all over again. What could you connect this to? I don't know, maybe an instrumentation amplifier, okay? Because you want to know this voltage, right? So you have that done as well. You just need to spend 3 cents on a photodiode. We have everything else we need already in hand. And now you can measure the light. So this is what you might see. Here's time. Duck. And this, I'll call it VL, for the voltage coming out of the light. Okay? Now let's say first the light source is off. So here the light source is off. And then we turn it on here. Just kind of stays on. And so what you're going to see, switch to another color, is that here there's no voltage, right? Because there's no light, right? You can say maybe there's ambient light, sure, but there's no light coming through, so you're not going to pick up anything. But then the second you turn it on, you will see this big jump in the amount of voltage that you detect, right? Because you'll see more. So that's interesting. Now you're taking this and you're just, you're looking at it over time. Maybe you're plotting it, as you know how to do now. And you notice something interesting. You notice that sometimes, every now and then, the amount of light you see drops. And this drop happens, well, I don't know, about once a second. Drop, 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 boom, boom, boom. What are you detecting? Any idea? What? Could be noise. Boom, 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 right? I'll give you a hint, because it's not necessarily obvious, right? Remember what this thing is called? It's called a pulse, right? Because that's what we're talking about. We're talking about we're going to explain how a pulse, and then it is an oximeter, like an oxygen meter, right? Notice that the pulse is built into it. It's like you get it for free, right? When I did this, I didn't just get my blood oxygen level. I also got, it's interesting, get heart rate. You know what else can measure the heart rate? All your smart devices can measure heart rate, right? What do you think? Okay, I've teed up this now. What do you think these blips might be? Yeah.
The flow of blood.
The flow of blood, that is associated with each heartbeat. So your heart beats. Some blood vessel in here. And every time your heart beats, well, of course, what's that beat is specifically it's like a pump. It pushes blood through your whole body So it's sending blood into your finger. And for some reason, every time the blood fills your finger, the amount of light that you detect is less. So you can imagine, I have the light, right? Beat. Somehow less light gets through. Beat. Somehow less light gets through. This is a and now, well, if each one of these is a beat, I'm going to go switch back to blue. Then obviously this interval here, right, is the time of interbeat, and you can calculate heart rate. And that's how it does it. That's why it has to shine light. If you look closely, it has to shine light. And if you put something between this that blocks the light, it's not going to work. Oh. Now, I'm going to explain to you how it works. I think you almost know already, right? It's because it's clear in a sense. But let's talk a little bit more about it and how we get the oxy out of it as well. And you can say, but why do that? Didn't I show you earlier that this has, and you can do it via an EKG? You can. So for the EKG thing to work, I have to go to the EKG, and then it tells me to put my finger here. And the reason is that it's measuring the potential from this location to this location. As you know now, it's not going to be successful to measure an EKG from here to here. You have to go from here to here. Well, I don't have two watches and a cable that runs from this way to this way. So for the EKG, it's a little harder to get it via a watch. For the EKG, it's a little harder to put this and get an EKG. But it's not a problem here at all, right? Just put the sensor on anywhere you want. Right? You can put this on the ear, okay? And you will measure it locally. So that's a good trick. Okay.
Let's say someone's like fatter, so they have more fitness in their wrist. Would
Right.
it cause more noise? And if so, how would you get rid of that noise?
So the question is, if someone were, we don't say fat, we say plump or something. If someone were plump and then therefore have more fat on their body, how would it affect the signal, right? So it's not this finger, but it's a slightly bigger finger. And will that introduce noise? And we're going to talk about exactly that. Okay, we're going to talk about exactly that issue. At a cartoon level, might still work, right? I mean, there'd be less light going through to begin with, right? So maybe we start here. But in principle, it might work, but you're worried about noise. There's another big source of noise, right? So I have this, imagine there's a light sensor here, right? Here's my finger. Are there any other sources of light in the room, right, that might interfere with what's going on here? Of course. It's everywhere. And these lights, though they look steady, are not steady. They're flickering, right? And so the light level in this room is not steady. So in fact, this is, as you know now, never the case in biomedical instrumentation. We never get this. Instead, we're going to get a disaster. And that disaster is going to be, now I'm going to add V noise. I'm not quite sure how to draw it, but I'm going to draw it like, well, anyways, I don't know. Like that. And so the actual signal that we detect here, right, we're going to say our VT for V total is going to be the summation of these. I didn't do the ticks the same, but you get the idea. And it will look like right. You get the idea, right? If I didn't draw this accurately, right? This plus this gives you that. Okay. How many beats were here? 1, 2, 3, 4, 5. I don't know. The only reason you even think you might know is because you see this. But if I had covered that up and I said how many beats, and like you have to get it right, you might say, and this, by the way, if you're saying, well, is this how big the noise is compared to the signal? No, the noise is much, much bigger than this. Much, much worse than this. It's not even like this. Imagine this times 100 with 100 more wiggles, and this happens. And that's what's happening here. Huge amount of light is getting in. And it represents a major issue. But there is a trick. There's a trick. And the clue to that trick is if you looked, and I know you can't quite see it, but if you looked closely, and I welcome you to do it, at what was going on, oh, maybe we can see it. Hold on. Let's see if I can make it start. We'll see it. Let's see. It doesn't want to play with because it's off my arm. If you did look closely, you would see that the lights are actually not on, but they're flashing. So it looks like flash, flash, flash. Now, could you make a light that flashes? You could. If you had to figure it out, right? Maybe you apply like a sinusoid, or yeah, you could figure it out if you really had to do it, right? You could build a circuit where the light flashes, right? You could also build a circuit where the light intensity is oscillating very quickly, right? I want to start with this example because it's the one that we're a bit more familiar with. Okay, so now what's happening is that I'm going to say here, this is the eye of the source, the eye of the light source, right? This eye of the light source is in fact doing something like this, right? Okay, we're just going to go to the sinusoidal example because we're familiar with it, right? It's not a steady light, right? You're going to take a sinusoid and you're going to plug it into your LED. So what's the light from your LED going to do? It's going to go up and down, right? You know how to make this. Okay, why would you do that? Why would you do that? Well, what would you now see as far as a voltage as a function of light? Well, what you would see is an amplitude modulation of this signal, right? What you would see is an amplitude, what you would see, let's say what you would see is something that, I'm going to try to draw it out. It's going to look like, maybe once I draw it out, it'll be clear. I'm going to increase the frequency a little bit. I'm exaggerating this here, but it's a big exaggeration, but what you would see is that sometimes these voltage wiggles are very big, and then suddenly they get smaller, and then they get bigger, and then they get smaller. Why? Because a lot of light is getting through. Wiggle, 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 wiggle. Suddenly something is blocking the light. Less light gets through, smaller wiggles. Then the finger goes back to the way it was. Bigger wiggles. Is that clear? So if the beats are here. And we saw this before. We saw this with the lie detector. Because the exact same things are used across all biomedical instruments, and this is one of those exact same things. What did those two things have in common? All instruments look like this. And I told you that this is true. And we're not going to see a single instrument that doesn't meet this rubric, right? But it doesn't mean I'm not to add on a little bells and whistles. So the thing I'm going to add on here is an energy source. And then the body is here. Okay. So when you have a temperature sensor, we don't have an energy source, right? The body just puts some temperature out and we detect it, right? Or, right. But when we had a lie detector, if you think about it, we were putting voltage into the body in order to detect the resistance of the body. The lie detector doesn't work if we don't connect a voltage to your resistor. Now that may seem maybe a more of an abstract example, but here you're seeing it in a more specific example. The body, at least the way we're doing this, right, is not emitting this light. What we're doing is we're shining energy into the body. The body is then changing that energy and we're detecting it. And this is not a negative. This actually is a major positive because we control the light. And so what we do is, in practice, we pulse it, but in this example, we're just going to oscillate it. Because what that does is it makes the frequency, let's call it the carrier frequency to be clear, of the signal whatever WC we set, where WC, right, is the frequency of this signal. We determine the frequency of the signal. That's a good trick. You were born in 2001 and you want your signal to be at exactly 2001 hertz, you got it. You want your signal to be at 4001.5 hertz? No problem. Just make it flash at 4001 hertz. And now the thing coming out of here is right on 4001.5 hertz. What a trick. Now, do we still have the noise? We do. So the net signal, right, is going to be this plus that. I'll draw it. I mean, I'm not going to try to draw it accurately, but the net signal is, whatever we had here, but it's somehow, I don't know if me drawing it helps make it clearer, but this was supposed to be where we had the two blips, right? And so what you're seeing here is we sort of have this large envelope, then we have the small envelope. I meant to show you a large envelope, small envelope, large envelope, right? I'm going through this a little bit quicker now, but I did go through this for the lie detector, right? And at the time I said, you're probably not going to work with lie detectors. I don't think so. You're going to encounter pulse oximeters and similar technology for sure. And so now what happens is we have a situation here where the thing coming out, our V total, right, that's what we really have to work with, has signal, right, and noise in it. But notice that the signal, right, is at a single frequency of 4001.5. And the noise is, well, I don't know, it's at 200 hertz, it's at 10 hertz, it's at 6,000 hertz, right? Right? But there's not very much of it at 4001.5. Maybe there's some, but not as much, right? So now what do we do? How do we then separate out the signal from the noise? Bandpass. So then we're going to take this and we're going to send it to a band pass filter. And the goal of this band pass filter would be to just let this through. And what is that band pass filter going to look like? Now I'm going to draw it like this. Here's the gain. Here is frequency. Here is this peculiar WC, and I want it to look like this. Now, I hope you understand what I've drawn here, right? Because we spent a lot of time trying to make it clear what this picture means. You're saying that's not a circuit, it's a picture, right? But this is the picture of the circuit. This is what you care about, all right? This is what you're going to tell. You could give this to the AI and say, give me a circuit, okay? Because it tells you that it's going to have a zero gain everywhere except for your carrier frequency, right? So you see, when I'm describing what to do here, I'm not drawing resistors and capacitors. That's not the best language to talk in. Here's a resistor, here's a capacitor, 13. No. All I need to do is I need to show you this picture and you know what to do for a pulse oximeter. But this is the first time you're hearing about pulse oximeters, correct? The same principle that is used in every single instrument is used here as well. Low pass, high pass, band pass. There you go, right? There's your band pass. You see, it's the same thing. And then you will need to do this extra step where you demodulate it just to kind of get back this thing. And again, just refer to what you did, what we talked about before, or look it up. All right? These circuits are absolutely generic. They're what you would build anyways. Because in biomedical instrumentation, we just do the same things over and over again, which is great, right? But you can see the little variation here, right? So that's the pulse part, and that's why you know, and that's why it flashes, okay? Now, I told you we're going to be talking about how to measure how much of something, right? So we actually haven't gotten there, right? So, but this was the setup for it. This was the pulse in the pulse oximeter. And I need to mention this little bit about why the light is flashing. You with me? Yeah? Okay. Now let's do pulse oximeter. Okay. I need to tell you about something called the Beer-Lambert law or rule. Okay? This is what it says. If I have a vial filled with something, right? I like to say blood or something like that, all right? And I shine a light in, and that light has an intensity, what do I use for notation? I sub 0. And then I detect, and there's a lot of light. And then on this end, with my photodiode, I will detect the amount of light that comes out, which is equal to I. And there's some material in here, some material A. All right, there's something in here. And it's dissolved in water or something that's transparent to the light. Okay, but the material here is, and my question is, you know, how much of A is in there, right? Let's say it's like a virus, and I want to know, do you have a lot of virus? Do you have a little bit of virus? I want to know how much of this stuff. So now we're getting into the how much of something. There's an equation that says, we can figure it out, the I is going to equal, and this is Beer-Lambert, e to the 0 times e to the minus, we'll do it like this, A, where A is given by where A is given by the concentration, let's say the concentration of A, times something called the extinction coefficient of A, times something called L. I'll define what these are. So you could also have written this as I is equal to I sub 0 times E to the minus, let me just use C for concentration, C times this Greek letter epsilon times L. Okay. I mean, I think at first pass seems a little intimidating, but I don't think so. Let me point out what we know. All right, I'll put a little line over it. We know this because we put it in, right? This is, or let me put it here, right? We know this because that's what we put in, right? We know that, right? That's what we put, we control this. We know this one because that's what we measured, right? That's the thing we're measuring. So put a line over that so we have that covered. We don't know the concentration, right? That's the thing that we wanted to know. This thing E, let me write it out. So C is the concentration. We might use molar in that. L is the length. And which length we mean? We mean this length. Okay? And so that's going to be in units of, let's say, centimeters. Now, I know L because I have a ruler. Right? I have a ruler, or I just know that this was a 1 centimeter, so I have that. What about E? So E has different things. It'll be called the, it might be called the, absorption, or the extinction coefficient, and its units are 1 over centimeters. It has to be 1 over centimeters per molar. I just know that because the units have to cancel out, okay? And this we know because we're told. So if this is whatever it is, right? Whatever, some virus, some protein, whatever it is, this is a number that we look up. So if you look at what we have here, we have one equation and one unknown. And now I can tell you what the concentration is. Just as I go through this, you know, and I always try to present stuff to you, I think, in the simplest way possible. It means I'm sometimes leaving out little details, right? You'll sometimes see this instead of an E as a 10 to the power, and that's where people will move between different kinds of coefficients. So again, if you look, you know, when you're looking up on your own, you'll see some variations, but I think this is the simplest way to think about it, okay? So let's go through an example. I'm not even going to calculate out, but let's say I put in, I don't know what the units would be of let's say the light I put in, did I do that right? I0, yeah. So the light I put in has units of, without, I don't know what the units would be, has an intensity of 10. And the material that is in here has an extinction coefficient of 0.1, right, per centimeter molar, and the length is equal to 1 centimeter, and I happen to measure out 5, right? And I ask you the question, what was the concentration of it? But to be clear, this is the extinction coefficient of A, and this is also going to be the concentration of A, and you can calculate it, right? If it was a quiz and I gave you this, right? You might get this quiz in chemistry class or something. Well, there's one equation, right? You plug, 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 divide, natural log, get this out of here, right? A few more divisions, and you got it. And so you see now that you can measure the concentration of anything right? But you do need to know this value, right? If I didn't give you this value, you wouldn't get it, all right? You get it? I don't think, right? And we're back to this light, right? They would say, but I don't, this is a vial. Could be a vial. Could be a finger. Okay, now of course there's more to it than that, but you see where we're coming. This is the only equation you need to know for me to finish explaining how pulse oximeters work. So this is the only equation. In fact, for all, as far as I know, light-based, and it's not that bad. Okay, but I want to make sure we're all good on this. And then we're going to play around with this equation. So if you are willing to accept one equation, I can explain to you how to measure the concentrations of things using light. Okay, now, it turns out that if I have another material, and I'm going to call that material B, it is going to have a different absorption or extinction coefficient. It depends on the material. So coronavirus, whatever it is, right, versus glucose, is different. So they have different values. And so, in this example, let me go to same color, black, let's say. In this example, if I was looking at B and its extinction coefficient was 0.8, and I asked you what was the concentration of B, right? Well, don't be tricked. You better make sure you plug in the right extinction coefficient. Does that make sense? So it does matter. And you need to know one other interesting thing about these extinction coefficients. They actually depend on the color of light that you shine, which I left it up until now. So in reality, what we can say is, to be more consistent, let's say everything I said up to now was I was really talking about red light. So what I'm really going to say is, when I use a red light, right? So you see, the extinction coefficient depends on the material, and it also depends on the light. So when I use red light, and I was thinking about material A, then the extinction coefficient, I'll write here A at red light, that's what I meant by 0.1. And these numbers, by the way, are all made up, right? They're just simple numbers, so you can see them, right? And then for B, the extinction coefficient of B at red light was 0.8. So I need to be a little bit careful when I give you these extinction coefficients that I specify what light I'm using. If I was using, for example, green light, go back to this color, green light, then I'll have to say the extinction coefficient of A at green, some other number, 0.2. And the extinction coefficient for B at green was another number. Let's call that 0.01. Notice that this extinction coefficient went up, and this one happened to have gone down. And so if I give you this problem, and I say, I better be clear, right, that this was red light, right? And this was for red, and this one was for red. And if instead I said I shined green light, you would have to put in the correct values. I'm not trying to confuse you here. It's still the same equation. Right? It's still the same equation. Just, you're with me? Like, you just could have plugged in other stuff, right? It's not so bad, right? You just make sure that if I'm shining in green light and I'm asking you how much of material B there is, you use this parameter. Now, yes?
So far, the lights that we've had, they've always been the set color.
Yes.
The same device emit different spectra of light.
You can certainly have two LEDs, right? Which is, I think, what my watch has, and what this device has, where there's different LEDs, right? And now I'm going to explain to you why you would do it. Because there's a big difference between this vial and a finger. There's a lot of differences, okay? One of those differences is that you don't necessarily know the size of my finger. Because if I put this on me, right, there'll be a certain finger size, but if I put it on you, there'll be a different size. So we'll all have slightly different finger lengths, right? That's biomedical engineering. So I'm going to say, I'm going to go here, and I'm going to say, I actually don't know the length, right? And now you have a problem. I say put in 10, red. I'm looking for material A. Okay, do I have an extinction coefficient? I do, it's 0.1. How much did you measure? 5. Great. Tell me, please, what was the concentration of A? You have a problem, because maybe there's a lot of A. Or maybe there's a lot of material. Does that make sense? Make sense? Right? A lot of A or a lot of material, and you can't tell the difference. Oh well, I guess it's what we throw it all away. So now watch. This is very, very clever. Do it twice. First do it with the red, and then do it with the green. Meaning, what we're going to get is, we're going to do red first. I red, so I'm going to get some, this is all under red. Oh. The intensity I measure is going to be the intensity I put in at red, e to the minus concentration of A, because that's what I'm interested in here, times the extinction coefficient of A at red light times the length. Bless you. And these are the two unknowns, right? Let me put the unknowns, right? Unknown, can't see it, but yeah, unknown, right? Can't solve the problem. Okay, I'm going to do it again. Now I'm going to do it, I'm going to shine a green light. Red light, green light. E to the minus. Okay, now what are we going to write here? Let's be careful. It's the same concentration, right? But it's a different extinction coefficient. Now what's that? But it's still a number, right? It's 0.2, so let's not worry about it. It's just a different number. So we're going to do extinction coefficient of A at green, times the L. But I want you to notice something. Is it the same L or a different L? Same L. Same L. So there are here two, this is not an unknown. This is not an unknown. That's the thing you gotta understand. These are not unknowns. If they're unknowns, we don't do this. But they're knowns, like they're here. So now what do we have is remember, known, known, unknown, unknown. Two equations, two unknowns. And now we can solve it even though we don't know the length. So that is why we shine. And then someone asked me about what about plumper fingers, right? So now you can see, oh, okay, even if I had a plumpy and a less plumpy finger, right? I could do a trick where I do this twice. And guess what? They're all shining two lights. I don't know if you can always tell, but they're alternating between two lights. There's two colors. Now you know why there's two colors. Are they doing this trick? They're doing this trick. Yes?
It's like a two-part question. One,
Two-part question. Oh boy.
in the first two, would this be considered like a type of calibration? And also, why stop at 2 and not do like 3 here?
All right, so the question is this a type of calibration, and why stop at 2? At this point, we will get to calibration. At some point, we're going to have to calibrate. At this point, I do not need to calibrate because as long as I have these values, right, I don't need to run. Calibration would mean I would need to put in substances of known concentration A and B and measure the resulting light. I don't need that. The other question is why stop at 2, right? Well, in this case, I only need 2. But could do 3 and could do 4. So this is why you do 2 colors. You see? I think it's straightforward. Like I told you, I took this class. There was stuff that was explained to me. I don't know. I think it's just, there's like a complicated way to explain things, and then there's just this. It's just 2 equations, 2 unknowns. This is, and look, I'm only using this equation. I'm only asking you to accept this equation. And I'm asking you to do algebra. I'm not asking you for more than that. You still got to understand this equation, and you need to understand that this E here is a function of the color. It's really important that you understand that this epsilon, it's not bad that it's a function of the color. We love that it's a function of the color because that gives us our 2 equations. Yes? Okay. But our problems don't end there, right? What if there's A and B in here? So I know the length. You know what? Turns out I got a ruler, okay? So I could figure out or I have some clever way to translate angle to displacement. All right, let's forget that, okay? We know the distance. Or I built the device so it has a fixed distance, right? There could have been some other way to solve that, right? Or in this case, somehow I know the distance, all right? Fine. But there's more than one material in here. I mean, you think there's only one material in my finger? Right? Is there one substance in my finger? Is my finger just made out of A? No. My finger is made out of many substances, A, B, C, and D, right? So now we have another problem. But let's deal with that problem first with just A and B. So you have the vial. We know the length. We're good. We're good. Just want to forget that. Okay? Forget that. Right? Right? I know the length. But I have 2 different materials. All right? How do we, first of all, I need to show you what the equation for that is. It's the same equation. Good. But I need to add some terms here. What it's going to say is when I have 2 materials, I'm going to have to modify this equation. I'll do that just under it, where I is equal to I sub 0, nothing has changed so far, E to the negative, and now I'm going to add this term here. I'm going to say the concentration of A times the extinction coefficient for A, and this is at a particular frequency, okay, but I'm just writing it simpler like this, times the length plus the concentration of B times the extinction coefficient for B at a given frequency times L. You see, it's just like you have they just add up, right? They're just joining forces. What it means is you can think of the A is removing light and the B is removing light, and they're both going to remove the light. Because this is an exponent, you can actually break this up as to E times this times E times that, right? You can see that it's one cascading after the other. So this is the same equation. You just need to add these additional terms. And I will actually remind you, what symbol do we use? There's a big star here. to remind you that this here and this here are a function of the frequency that we put in. All right? Now, we can go back to this problem. I'm not going to rewrite it. I'm just going to kind of go like this, where we're back to knowing it's 1 centimeter. And I actually now want you to give me the concentration of A and the concentration of B. Well, we have a problem because let's say not a lot of light gets through. Is that because I have a lot of A and a little bit of B? Or does not a lot of light get through because I have a lot of B or a little bit? Maybe it's a little A, a little B, right? No. Maybe I'm mixing it up, so it's like 50-50. So say, well, let me just go to the only equation, right, that we're using. We'll put boxes. We have one equation. Let's think about it. Let's use green again for. So let's put a line over what we know. No, because this we put in, this we measure, right? No, put it under it. No. But we don't know C sub A and we don't know C sub B. So what you have here is one equation with two unknowns. That's why you can't figure out what C sub A and C sub B is. Right? How would you this could be a million and 0 or 0 and a million, you know, I mean, there could be different there's things it couldn't be, but there's an infinite number of combinations of things it could be. So when you have two materials in here, you seem to have a problem. I wonder if there is a solution. I wonder if there's some way where we could, instead of having one equation with two unknowns, we could have two equations with two unknowns. How can we get two equations? By using two different lights. And so now what we'd get, let me write it out so it's clear, is this. In the first case, we would get concentration of A times the absorbance of A at red plus the concentration of B times the absorbance of B at red times the length. I just pulled the length, it's the same length. And in this case, I would get concentration of A times the absorbance of A at green plus the concentration of B times the absorbance of B at green times the length. So I know there's a lot of terms here, right? But the unknowns are here. This is just a number, like 3, and these numbers, right? So number. All right? It's not that hard to solve this system of equations. You could do it, right? You could solve this system of equations. 2 equations, 2 unknowns. But if you didn't shine 2 lights, you would have 1 equation and 2 unknowns. Saying, oh, this sounds it's like the same trick we did. Yeah, it's the same trick, right? It's the same trick. We're shining 2 lights. But we are still only relying on this equation. I just wanted you to realize that this is how additional terms factor in, okay? So now we know how to measure the concentration of something. If we don't know the length, we can compensate for it, right? If we don't know if there's 2 materials, we can compensate for it. In fact, we're not going to deal with it here, but if you didn't know the length and you had 2 materials, well, you could use 3 wavelengths. Interesting, right? And it's all because we control it. So you see, it's not a negative. The fact that we control it, the fact that we could, for example, modulate it, the fact that we can set the color of it is a huge plus. It's a huge plus, right? So long as we know how to do it. And so what you're getting here is from concentration, right? So you could measure the concentration of things. Now, how far are we going to get? All right, what we're going to do is we're going to pause here. I'm going to give you a hint. What I'm going to tell you in the next class is there are two materials. Oops. One is called oxyhemoglobin, and one is called deoxyhemoglobin. There's these two things that float around in your blood. This one just grabs oxygen to become this, all right? And in fact, this thing that comes out, this SpO2, is the concentration of HbO2 over the concentration of HbO2 plus the concentration of Hb times 100 to give you the percentage. So there's like a total amount of this stuff, right? So let's say there's 10 to work with. So maybe you have 9 of this and 1 of that, right? So it'd be 9 over 9 plus 1, 90. You're at 90%. Good for you, no hospital. Let's say it's 5 and 5, right? 10 total, because we get the same amount total, 5 and 5. 5 over 5 plus 5, right? 0.5 times 100, 50%. Hospital. That's like ambulance, right? Or I don't know, dying? I don't know what that.
92 is the threshold
What's
for
the-
needing oxygen.
Which is?
If your SpO is 92 or lower,
Then you're bad. Okay, so not even 92. Thank you for that correction, right? Adrian's an EMT, so he would know better than me. So that's why when I get this oxygen reading here, right, and when it says SpO2, it comes out as a percentage. It's a percentage between this and this, and it is really important, right? Adrian, I'm sure this is like the first thing you put on someone when you wheel them in. Oh, you have one on you. Wow. It's the first thing you do. And during COVID, everyone was buying these, right? Right? When this goes bad, it's when they respirate you. Then you're in trouble. So it's a really powerful measure. Huh. So you're measuring the concentration of one thing. There's another thing. You see how I'm setting you up? Okay, so what we're going to learn next time, and also remember here, remember what caused this blip here? You said it was the flow of what? Blood. So, oh, this is blood. Oh, that's blood. That, see the pieces, there's something, it's all there, right? We just have to put it all together. Oh, so this is blood, and then we have a way to do a chemical analysis of it. And what we're going to do next class is I'm going to walk you through all the math. And here's a hint. At the end of all that math, right, which I don't remember, right? So it's going to be 1, 2, 3, 4. Right? I worked this other weekend. I took my kid to a Pokemon tournament on Sunday. So just like standing around for like many, many hours. So I just wrote it out so I'd have it in front of me, right, to write it through you. Here's a hint. Once it's all done, you can forget all of it. Because in practice, instead of using math, guess what they do? Adrian, what did you say? Actually, asked about earlier. What do they do at Apple and at whatever company makes this, right? And whatever Massimo, whatever it is. What do they do at the end of the day after they make these things? What did you do when you made your thermistor? Did you rely on the math? No, you calibrated. So going back to your question, we're going to go through all this math, and then I'm going to say, guess what? Very nice. People don't actually trust it, so they actually end up just calibrating these things out. And so you won't even need to know all this math. But I think it's still kind of cute. Because it kind of brings these ideas together, so you know, oh, I see how the math is. We're just going to use this equation. I'm not going to introduce any more equations, all right? So that's for next class. For this class, I need you to understand this so that, I don't know, what if I did give you a quiz and I asked you any kind of thing like this? I wouldn't feel bad if you couldn't do it because supposedly you were paying attention. Correct? You could do simple Beer-Lambert calculations, okay?